We're given an array of integers and we want to return indices of the two elements that add up to target. 2 and 7 add up to our target 9, so we return the indices for 2 and 7, which are 0 and 1. There's exactly one solution, and we cannot use the same element twice. We're given an array of numbers, but the underlying question is about pairs of numbers. So this raises a question, which is, how can we turn our array of numbers into pairs? I'm going to try thinking about this with a concrete example. Imagine an array with 4 elements where these are the indices. Starting with index 0, we can pair it with 1, 2, and 3. Index 1 has already been paired with 0, so we just need to move forward to 2 and 3. Index 2 has already been paired with 1 and 0, so we just need to move forward to 3. By the time we get to index 3, it's already been paired with all the previous indices. So for each index, we just need to pair it with the indices that follow, and that will give us all the possible pairs. Now that we've generated all of the pairs, I want to turn this diagram into code. And in my head, I'm actually imagining it being pulled apart vertically. And I'm noticing that if we represent the first element in each pair with I, and then the second with j, we can see that these are the i's, and then these are the j's, and the j's always go from I plus 1 to the end. Now in our code, we want our I to go from 0 to the end, and then for each I, we want j to go from I plus 1 to the end. Then we just need to see if the current pair adds up to the target, and if so, we return. Our space complexity is O of 1, and for time, the outer loop runs n times, and a lot of people think that the inner loop does too, but that's not true. This is a really common misconception. Here's what's really happening. The inner loop always runs a different number of times. We know that from this diagram where it runs 3 times, 2 times, 1 time, and then 0 times. So it starts from n minus 1 and then goes down to 0. If we consider a bigger example where n is 11, we can see this pattern more clearly. The inner loop is going to run 10 times, 9 times, 8 times, and so on, all the way down to 0, and if we average all of these, we get 5, which is about halfway, or n over 2. So for our time complexity, that gives us n for the outer loop, times an average of n over 2 in the inner loop, and that becomes n squared over 2. And then in big O notation, this simplifies to O of n squared. O of 1 space is great, but n squared time isn't. So I'm wondering, can we do this faster? We can't avoid examining every number at least once, so we can't do better than O of n, but we may be able to optimize what we do with each number. And when optimizing algorithms, I like to ask myself, could perfect information help? And this often helps me see new ways I can exploit the underlying data. So let's think about what's happening at each step. So when I see a number, I want to know if it's part of the target pair. And if we had perfect information, I'd also want to know the other number we would need to form the target pair. And then of course, we'd also want to know if we have that number available. For number 1, it's relatively easy. We know that the current number plus the number we need will be equal to the target. And so if we do a little bit of algebra, we can see that the number we need is equal to target minus current number. For number 2, a new question comes up, which is, can we structure the data so that we can quickly see if we have number needed? And if I think through all the data structures, I can see that a map can help us do that. If we store each number as a key, we'll know if we have number needed in O of 1 time. That would give us O of n time overall, and then we would need O of n space for the map. So we know we want to store each number as a key, but what do we store for the value? It could make sense to store indices since the question says we need to return indices anyway, and then we could use those indices to make sure that we don't use the same element twice. But a number can appear multiple times in the array, so do we store all the indices where that number occurs? That could be complicated, and the time and space complexities are not obvious. Now, storing just one index would be our other option, it could simplify the mechanics a lot, but it's not obvious it would work. And if we did, which index would we store? Now, when building the map, the most obvious thing would be to do something like this. So we initialize the map, loop through the numbers, and then save each number as the key and the index as the value. And if we see the same number again, we'll overwrite the old index with the latest one. And that means by the end, the map will only have the last index where a number occurs. Would this approach work? Let's look at an example. We have 5 for 6 and the target is 10. If we generated the map, it would look like this. Remember, the keys are the numbers, and then for the values, we have the last index where that number occurs. At index 0, we can see that we need a 5. The map does have a 5, but it's at our current index, so we can dismiss it. This means there's no danger of using the same element twice. Then at index 1, we have a 4 and we need a 6. We check the map and there is a 6 available, so we return the indices 1 and 2. Now let's make sure it will still work when we actually do want to use 2 of the same number. So I have a really similar example. The target is 10 again, but the numbers are 5, 4, 5. So we want to use 2 5s, which is okay because we actually do have 2 5s available. So let's construct the map. We record a 5 at index 0, a 4 at index 1, and then another 5 at index 2, which overwrites the old value. Now that the map is built, we can look at each number. At index 0, we need a 5, which is in the map, but this time it's at a different index, so we can return 0 and 2 as expected. So this shows that we can correctly identify cases where we do need to use 2 of the same number, and that's because conceptually, in this type of situation, we'll always compare the index of the first occurrence against the last one, and we can concretely see that in action. We stop at the first 5 index 0 and check it against the map, which has the index for the last 5 index 2. Now that we know it will work, let's move on to implementation. We've already built our map, and then for each number, we want to compute number needed, and then we have to see if it's in the map. We also want to add a check to make sure that we don't use the same element twice. And if we pass these checks, we return the pair. There's also, unfortunately, a syntactically shorter but conceptually more complicated solution that everyone thinks is good. And this is a classic case where people are failing to fully consider clarity and mental overhead. And honestly, the real reason it comes up so often is that people are just repeating it after having seen it before. So to be clear, I don't like this strategy, but since it is so prevalent, I'll describe how you could come up with it on your own without having seen it already. Realistically, you would have to get the 2-pass map strategy that we just went through first. That's because the most obvious way to use the map is to answer the question, is number needed anywhere in the array? Because we're asking about the whole array, we need 1 pass to load the whole array into the map. And then after you get the 2-pass strategy, you would have to ask, can I do this in 1 pass? This is kind of a nonsense question though, because making it 1 pass will not improve the time or space complexity. But you'd have to hold that thought and keep going anyway. To combine the 2 loops into one, you have no choice but to create the map and check the numbers in 1 loop. So we'd have to combine it like this. So here's our starting point, the 2-pass map strategy. So I'm going to move this line into the second loop, and then we can get rid of this first loop entirely. Now there are 2 really important notes on this. First, you have to have the insight behind why this line has to be at the bottom of the loop and you cannot put it at the top. And then second, we actually don't need this check anymore, so I'm going to get rid of it. And I'll leave it to you to think about why these 2 things are true. A lot of people take details like this for granted, so interviewers can easily push at these things to figure out if you actually understand what you're doing or if you just memorize the answer. That's why it's really important to think about it on your own carefully. The big difference though is that before in the 2-pass, when we looked for number needed, we could trust it because the map contained the entire array. But now it doesn't. At each point, it only contains numbers that we've seen already. So that raises an important question, which is, will it work given that the map is missing information? And this is hard to answer because it requires thinking about the problem from a very different perspective. And here's how I thought about it. Assume the target pair is x, y, and x appears somewhere before y in the input. If the number is not in the target pair, we'll just store it in our map as we go along. So after the first iteration, our map only has this first item. So we continue and keep storing elements, until we hit x, the first element in our target pair. At this point, we want y, but it won't be in the map because we haven't come across it yet. So we have no choice but to treat x like any other element and keep going. Now, by the time we get to y, x will be in the map because we saw it already. It's guaranteed to be in the green by this point. It took me a lot of effort to see this perspective because previously in both the brute force and 2-pass map strategies, we could return as soon as we saw x. Now we have to dismiss x even though we know it's part of the result, and we have to wait awkwardly until we see y. Perspective shifts like this are really hard to pull off, and that's why I think this approach is actually pretty bad. The only time I would go with the 1-pass is in the rare situation where performance is so critical that using big O notation is too crude and we actually want to drop down to the individual instruction level. That's because the 2-pass will always look at all the elements to build the map, while the 1-pass might only look at some of them. So there's a small time and space savings that's not captured by big O notation. We talked about a lot of details, but I want you to focus on the questions we asked because that's the most important part. These questions gave us the crucial structure we needed to discover the solutions on our own, and they came as a byproduct of just thinking about the situation deeply. For example, at the beginning, we wanted pairs, but we got an array, so we asked, how can we turn our array into pairs? And then we had a brute force solution that was slow, so we asked, can we do this faster, and could perfect information help, and so on. So in a way, if you're a careful observer, you can get the key questions for free. And because of this, you can rederive the solutions whenever you need to without having to remember anything at all. And so not only is this the key to discovering the solutions in the first place, but it's also the key to studying in a way where you functionally can't forget anything. And that's what makes this so powerful.